let you take it away, Karl.
Thanks. Yeah, so I will be talking about ACE, which is our system to enable more complex smart contracts by executing them concurrently. And this is work together with Sinisha, Silvan, Kari, and Serjan. So I assume all of you know what smart contracts are. I'll still give a small recap. So essentially, they are programs that kind of run on the blockchain, which means that they have an account that they own where they can receive currency, send currency, and they can also store some state. So they have persistent storage. And this is very useful for many things because it basically allows almost arbitrary business logic to run on the blockchain. And essentially, this gives you a programmable bank account, of course, not at the bank, but on the blockchain. And Ethereum supports Turing complete language, which in theory would mean that we can do any computation that we want. But in practice, because of the execution model, everyone in the system needs to execute every contract call to verify the transactions. And this inherently limits the complexity of smart contracts. Because this basically means that all of the transactions are executed sequentially. And for example, if we have 10 transactions that we want to execute per second, this would mean that the theoretical limit for execution time for each individual transaction is 0.1 seconds. Of course, in practice, this is even lower because there are different overheads and you don't want to spend the whole time executing transactions for some security reasons. But this is kind of the upper limit. So with sequential execution, we can have at most as much execution as we can fit into well, time. So in 1 second, you cannot have more than 1 second of execution. And our goal was to enable more complex smart contracts. So this is, for example, interesting for some cryptographic protocols where you might have more complex computations that you may need to do, which are currently not necessarily possible in Ethereum. And the basic solution for this is don't make everyone execute the transaction. So basically, we want to have somebody execute the transaction, but not everybody. And this has also been considered in other work, which I will just briefly cover. So one recent work is Ekiden, also from IC3 researchers, where the idea is to execute contract calls in a trusted execution environment. And now the goal of this was mainly for privacy, but this can also be used for scalability because if you have a trusted execution environment, you don't need to execute it everywhere anymore. So you can use that to actually scale this. The main issue with this, of course, is that recently there were many vulnerabilities discovered in trusted execution environments, namely in SGX. And if you consider the break of such trusted execution environments, then this system will break down because it no longer guarantees integrity for the execution of your contracts. Another recent work was Yoda, where the idea is to execute the contract call in a randomly sampled subset of the consensus nodes. And this also means that no longer everyone needs to execute this, but only a part of all of the nodes. However, because this is done with random sampling, there still needs to be quite a lot of nodes that execute it. So Yoda can effectively reduce the number of nodes that execute the contract from a few thousand to a few hundred, and they might need multiple rounds of execution before it can actually be committed. So this can improve the problem a bit, but it still needs quite a lot of redundancy. And the last one, and this is the one that's most closely related to our system, is Arbitrum, where a contract creator can choose a set of nodes that execute the contract. And in Arbitrum, this set needs to have unanimous agreement on the execution results for the results to be committed. And if one of these nodes disagrees, then there is an expensive protocol for conflict resolution. So basically, there's a challenge period, and during this challenge period, no other contract calls involving this contract can be executed. Another issue that these solutions have is that a contract cannot securely call another contract atomically. So in Arbitrum, for example, if a contract wants to call another contract, this basically is the same as the contract issuing a new transaction, and this transaction will be executed in another block. So this cannot happen atomically. And our goal was basically to allow this safe cross-partition execution of transactions. So that brings me to kind of our system. So similar to previous solutions, we want to decouple the execution from consensus. So we also execute the contracts by a set of service providers that is chosen by the contract creator. So this gives us a flexible trust model similar to Arbitrum, but we don't require unanimous consent. We just require a quorum to agree on the result. So basically, we need a quorum that signs off on the changes, and then we will accept them. And of course, we also want to enable secure cross-contract calls. And for this, we use some techniques from deterministic concurrency control that we can make this efficient and secure. So our system basically, or the system model basically looks like this. We have some clients that can act as clients of a contract or also as contract creators. We have miners that are responsible for the blockchain consensus, and we have service providers that can be chosen by contract creators to execute contracts. Yes, and they all communicate over a peer-to-peer network, so we don't need any additional communication. This all goes through the peer-to-peer network. And basically, the way this works is that the client first submits a transaction to the network, and this will be collected by miners and get ordered in blocks. However, the miners do not execute the transactions. They just perform some basic checks, for example, that the transaction is formed correctly, that it has a signature from the client that submitted it, and so on. And this gets collected in a so-called ordering section in the block. And this determines in which order the transaction, in which logical order the transactions should be executed. So this basically gives a serialization of the order. And the service providers then execute the transactions in a partial order. So all of the transactions that concern one specific contract are executed in the order given in this ordering section, but transactions concerning different smart contracts can be executed in parallel. And after the execution, they sign the results and submit them back to the network. And there they get included in the result section of the block of some future blocks. So this is why the system has the asynchronous in it, because basically from when it gets ordered to when the results get included in a block, this can take multiple blocks. So how this looks in detail is now if we have Alice who wants to call a contract C1, that in this contract call will call a contract C2. So here we have this epsilon C1 is the executing set for contract C1. Epsilon C2 is the executing set for contract C2. So P1 and P2 are the service providers responsible for executing C1. And here we have a quorum of 1, which means that as soon as one of them signs the results, they will be accepted. And P3 is the executing set for contract C2, and there we also have a quorum of 1. So Alice sends a transaction to the network, but before she does this, she actually locally executes it to see which contracts are involved, because the contract call that she makes is a contract call to contract C1, and then C1 calls in that call C2. And she does a so-called reconnaissance step, where she first locally executes these contracts based on the known state. With this, she figures out that contract C1 and C2 are involved, and she attaches this information to the transaction. The miners then include this transaction in a block, and the service providers fetch this block from the network. The service providers also get uncommitted results from previous transactions of the other contracts from the peer-to-peer network, which means that P1 and P2 get results for contract C2, and P3 gets results for contract C1. With this, they can recreate the state of the other contract, which allows them to execute the full call chain. So both sets of service providers execute the full call chain, so everything that C1 and C2 do. And in this case, P2 fails, but this doesn't matter because the quorum of 1 is enough. And so after this execution, they will sign the results and send them back to the peer-to-peer network. And there they will be included in a block and broadcast to everyone. Yeah, and I think I should go to the questions now, so I won't go into more detail here, but please let me know if you have questions.
Anyone have any? Actually, there was one in the chat. I think I saw somebody. No, never mind. I think you have time for probably 2 or 3 questions easily. So if you have any, you can raise your hand and we can unmute you, or just type it in the Q&A section. I guess I can ask you one. So Karl, so in the previous slide, in the diagram you made, are the uncommitted results from the service providers on their contracts? Like is it previous transactions they've executed but that have not been committed yet?
Exactly. So uncommitted means that they haven't been included in a block yet. So for example, if in the logical ordering, contract C2 has another transaction that they need to execute, but they haven't executed it before it could be included in another block, the execution of this contract call should still depend on that, because it might have changed the contract state.
I see.
So these results basically get broadcast in the peer-to-peer network, where also the miners will collect them. So this is basically these results here from a previous contract call.
And so actually, you're also saying about the quorum there being only a quorum of 1. And so what is your adversarial model that you're dealing with? Like, is anybody actually verifying the computations?
So this is actually a good question. So the model we have is basically that the per contract trust model is chosen by the contract creator, and then the participants basically agree to this trust model once they use the contract. So this is similar to in Ethereum, you have the contract code, and you only participate in a contract if you agree with the contract code. And here, the specification of the contract, in addition to the code, also includes the set of service providers. Okay. So if I participate in a contract, I agree with the set of service providers and the quorum threshold. And this quorum threshold, this can actually be set arbitrarily. It just changes the preference in whether you prioritize safety over availability or vice versa. So for example, if I choose a set of service providers, let's say I choose 3 parties and I trust all of them completely, then I can set the threshold to 1, and this will give me the best availability, because maybe the service providers, or maybe I know that the service providers are not always online, but I assume that always one of them will be online. So this would be fine for me. Okay. On the other hand, if I assume that only a majority is honest, then I could choose the threshold at 2. So this basically gives me a lot of potential for choosing different trust models, basically.
Okay, and we have one more from Jason in the chat asking whether this looks like the consensus used by Stellar, as in, and do you choose who forms the consensus or who to form the consensus? Maybe Jason, you can unmute Jason for explaining this a little bit, perhaps better than I'm reading it.
So is it clear, or should I elaborate more?
I would elaborate more, just a little bit.
So, because the way I think about it is, right, so it's like you kind of choose, if I understand you correctly, like you choose who will be executing this smart contract. So basically who to form the consensus. This is just reminds me of like Stellar's consensus, like these are the set of people that you trust. And so I just want to see if there's any connection, or that, like, whether it will be helpful for us to understand your mechanism.
Yes, so I think the connection there is also that it gives a lot of choice to the users, but it's different in the sense that here this is done for each smart contract, and in Stellar this is done for the consensus. So in Stellar you have this federated consensus where you basically choose who you rely on for the consensus mechanism. And what we do here is not a consensus mechanism. So all of the consensus comes from the underlying blockchain. So this works with proof of work consensus. This works with BFT. This is arbitrary, because basically what the service providers between themselves don't run any consensus protocol. The consensus comes from the ordering of the transactions, and then we have deterministic execution of the smart contracts. And then all that the service providers basically provide is the statement, yes, this code, when we execute this code, we get these results, basically.
So does that mean that the kind of the execution of the smart contract and the consensus, but maybe the verification of the outcome of the execution is kind of detached somehow?
Hey, Jocelyn, actually, I don't want to interrupt, but we do have to move on. Next call. I'm glad you have a lot of questions about it. Maybe you guys can continue it offline.
All right, thank you.
Yeah.